All right. Hello, everybody. Are we good with the mic? Happy days? All right. Can everyone hear me? What about people in the other room? Can you hear me? Cool. Well, I'm assuming that's working. So welcome, everyone. Thanks for joining me today. We're in Pillar, so that's cool for the room. I did want to thank Stir Trek for putting this on. This is a pretty cool event. Not often do you get to see your slide deck 3 stories high, so that's fun. It'll be good because there's a couple of detailed diagrams in here that will now be bigger than an elephant. All right, so top 5 architecture patterns. If you're expecting a different talk, you can leave now, but that's what we're going to talk about today. So kind of the subtitle here is, adding tools to your toolbox. And when I was working on this talk, really what I'm hoping that you get out of this is an understanding of just the general types and why they're valuable and what's different about these different architectural types so that you can, when you're out in the real world, pick and choose pieces of these architectures. As we continue into the world of the cloud, things are getting more and more complex, right? And so being able to pick out the right architectural pieces to fit whatever your business problem is or what you need to solve is valuable. And so this is really about how do we talk about software and software architecture. Back in the day when we were just writing classes, the Gang of 4 came out with design patterns, and that blew everyone's mind. And we talked about factories and how we use those, and it really elevated the discussion because we abstracted away the details around those particular patterns. And that's kind of what my goal is here today, is to kind of elevate the discussion and be able to talk about architectural patterns and their pros and cons so that we can have an easier way of discussing the problem. So shameless plug time. I work for HMB, and we are having an event in September, and it is not a recruiting event. It is just a community event where you can come and pair up with somebody and do some cool coding and win some prizes. So we have a booth here. If you guys want to check it out, there's a thing at the booth you can scan and kind of register. Cool. All right. So me, I'm Jim Everett. I am a developer, architect, software enthusiast. I've been doing this for a long time. I'm 40 now, so yeah, long time. I have 2 kids. They're fun. They take up a lot of good time, and I've been doing architecture for a while, and that's my stuff. Okay, so this is a kind of interactive session from the perspective of throwing out questions as I'm going to go through each architectural pattern and then kind of talk about the pros and cons, and if there are any questions, you guys can kind of throw them out to me, and I'll try to talk about them to the best of my ability. This is a rather large theater, so I will kind of try to time this well. But does anybody have a particular favorite architectural pattern that they like to use? All right, this is how this is going to go. Cool. So, so microservices is hot, right? So we'll talk about microservices. Okay, you like the decorator pattern as far as the software pattern? Cool. All right. All right, so what we're going to go over today is we're going to talk about layered architecture. We're going to talk about event-driven architecture, microkernel, microservices, and space-based. As we talk about each one of these architectural patterns, they will often have different names, so we'll kind of talk about what those different names are, and kind of the pros and cons of them, what they are, how they're valuable, all that kind of good stuff. All right, so we start at the beginning, the layered architecture. Tasty, good, right? As new software developers, I think we often get this as kind of our introductory pattern. It's an easy way to think about software, right? We're dividing these components into layers. Think of them as like horizontal layers, just like this cake. And we usually have like the presentation layer, the business layer, the persistence layer, and the database layer. So the intent here, right, is to encapsulate and separate out the concerns as it relates to dealing with the database and the persistence, or the business logic, or the presentation layer. So when we think about kind of a normal web application, we think about, we're developing the UI, maybe we're working in JavaScript, and then we have kind of a separate business logic, maybe services, and then those services are talking to maybe a repository or something that's mapping our objects into how they're going to be persisted, and then there's a database or some sort of persistence store. So the real value in this, right, is that we're isolating out all the stuff that's related to the UI or all the stuff that's related to the business or all the stuff that's related to mapping, all that kind of good stuff. I think most people are pretty familiar with this. As I was developing, making additions to this particular presentation, I put this slide in here last night, but I don't know if anyone's ever heard of clean architecture before, but it is a kind of subset of the layered architecture. I really like calling it the hexagonal architecture because it makes me sound smart, but it's also known as onion architecture, all that kind of good stuff. The real purpose of this, and we'll get into some different diagrams here, but the real purpose of this is to align what the dependencies are between kind of your classes. So we take the bigger concept of a layered architecture. We're separating stuff out into individual layers related to their particular concern, and we take it a level deeper, and we talk about, how do we keep independence from particular frameworks? I don't know if anyone's ever done like web form stuff back in the day, but it got pretty tricky where you were doing event handlers and doing business logic within event handlers because you were super tightly coupled to Microsoft's web framework. So how do we become independent of frameworks, independent of the UI stuff, independent of databases, independent of external integrations, and testable? So this is kind of what that clean architecture looks like. I like this visual because if you think about all the dependencies are pointing inward. So the entities in the middle, your enterprise business rules, are rules that kind of go across your entire enterprise, right? They're kind of core to how your business works. The use cases are, what is my application solving? And then we have the interface adapters that are taking in requests and mapping them to this, basically our domain. And then on the outside, we have frameworks and drivers. So if you think about a web request coming in, right, we have an HTTP request that comes into us. We usually, whether Java or .NET or pick your technology, right? We have some sort of mapping that's happening. Usually it's magic to us, right? Like I got an HTTP request in, it's some sort of get or post, and there's information and it shows up in an object, right? That is the translation that we often have in controllers. And then what we usually do there is make it into a business object, pass it to a service to do some work. And then that service, may have entities that are related for, our entire business, and so we'll use those entities to kind of make decisions. So this is somewhat abstract, but this is, hopefully you guys can see that. It's a little small, but this is how I kind of break up projects now that are layered as this kind of clean architecture. And the intent of this is to show like actually how projects and dependencies are flowing. So at the top, we have this idea of a host. And when you think about a program and you think about it in the abstract, I always had the problem when kind of defining architecture, like it has to start somewhere, right? Like we have all these cool ideas of like, oh, there's going to be a microservice over here and a microservice over there, and people are going to be interacting with it, and you're like, okay, but something has to execute, something has to start it up. So for like a web application, we're going to run a process that's going to be inside of a web server, and it's going to receive requests. And so when we're developing that kind of controller logic, it ends up in its own kind of project, and for the .NET world, like a DLL, right? So then we have kind of what I call core, and this is where all the dependencies kind of focus in. So I tried to align the colors here with the kind of rings in the onion clean hexagonal architecture there on the right. So the blue is like the web, so that's our framework and drivers, and our interface adapters is the controller. So that's all encapsulated within one like project. And then we have the core project and an infrastructure project. And so I like these ideas because it makes it a little more predictable as far as how do I actually plug all this stuff together. You know, when I was starting out in the industry, we had this idea of separating it into different layers, and then we had interfaces. I don't know if anybody kind of went through this kind of same evolution, but everything was all in one project when we started, and we're like, this is too crazy, we can't deal with complexity, we're gonna break it out into layers. We break it out into layers, and it's a leaky abstraction because we have like objects that are coming out of the database, and those go through all of the layers, all the way up to our controllers. And so we have these nasty dependency graphs that are like, my controllers are depending on my persistence mapping layers, and it gets very complicated. So this type of like design as far as how to implement a layered architecture, I think is nice from the perspective of the core knows nothing about the outside world. It owns the interfaces to the services. It owns the interfaces to the repositories or to external gateways. And we have these other projects, right? Like host has a dependency on core because it needs the interfaces, right? We're using something like I like to pull the bootstrapping out as a particular project because that way we can kind of encapsulate all the dependencies. So again, we kind of think about dependency injection and IOC containers, and we're like, where do we put that? And that usually ends up in the host, which means the host then has dependencies on all the projects because it needs to say what's implementing this particular interface. Pulling that out, I think, makes it a little nicer because then you see very specifically the host is dependent upon the core is dependent upon the infrastructure is dependent on the core as well because it's implementing those interfaces, and then we kind of go out to the outside world. So layered architecture, kind of how to put it together, nuts and bolts style. All right, so what are the pros and cons of the big layered architecture? So it's a good general purpose pattern. I think most people understand it. It's kind of easy to understand. It's a good starter architecture for people that are coming into the industry. It is not without its faults. There is the sinkhole anti-pattern, and that's a great name for a concept that I think anybody that's implemented this layered architecture has seen, where you have to follow through the layers. And sometimes you have a layer that's not doing anything except for calling the next layer, right? And then, so you kind of like, it feels useless, and it is somewhat useless, right? There's anemic domain models, this idea of, you have a business logic layer, but all it's doing is calling your repositories. And then your repositories are calling your database, and your database contains all your business logic. Not super easy to test. So watch out for that type of stuff. There certainly are going to be opportunities, or there are going to be times when you're just going to have to pass through. That's just the world we live in, and I'm hoping that, I'm hoping everyone kind of understands from this talk that none of these architectures are going to fit any one problem perfectly, which is why we're talking about multiple. Every business problem, every particular need that you have in software is going to have its own little custom solution, and that's hopefully why they're paying us, is because if they just, were doing the same thing everywhere, then they wouldn't need all of us to go to conferences and spend a day hanging out and watching movies. Yeah. So this is best suited for kind of like monolithic applications. As we get into some of these other patterns, architectural styles, you're going to see, flips back to this, right? This is a pattern, an architecture pattern that is useful. But if we're talking about it on the big scale of like a single application architected in a monolithic way, a layered architecture, it's always a good place to start. I think when doing any sort of architecture or software development, very much the DevOps ideas of, we're going to be continuously improving from the feedback that we get from our environment is the tack that you should take, right? This is the easy way to start out. If things start to get icky and not working for you, take the feedback and kind of adapt. So each one of the architectural patterns, we're going to go through kind of these 6 different categories on whether it's good or bad. So for the layered architecture, agility. In an ideal world, we think that it would make sense that any change to a particular layer is isolated because we have that separation of concern. Each horizontal layer represents a different kind of mini domain, UI, database, whatever that be. But in reality, if anyone's ever implemented this, you make a change to the database because you need a new field on your page, or you need a new attribute in your API, and that means that you're making a change to the UI layer, or the layer that's giving you data, and then to your business logic layer, and then to your data access layer, and then to your persistent store, your database. So because of that kind of monolithic nature and everything has to pass through each one of the layers, it's not particularly agile as far as making changes. So ease of deployment, this sucker is everything goes out all at once, right? So it's not particularly easy to deploy because small changes, they all have to go out together. Testability, if you have good separation between those layers, it's easy to mock up. If you end up in a situation like I was talking about before about an anemic domain model, like your business logic layer is not doing very much, then testing it is not going to give you a whole lot of value. But if you keep those solid lines or solid separations between your layers, you can mock stuff out and make it easy to test. All right, performance. This one's not particularly known for performance because you kind of have to do pass through each one of the layers. It's kind of I don't know. It's not maybe the best example of why it's not performance, but it's not usually particularly performant as an architectural pattern. There's no way to kind of add extra performance to it. Scalability, because it's a monolith, it's hard for us to scale. Ease of development, it is easy to understand, and so it's easy for your team to grok, and it often kind of follows how we do business, which is kind of Conway's law, which is that the communication patterns in your organization end up in your software. And that's usually how we kind of talk. Like our departments, sales talks to this department, talks to this department, talks to products department, talks to compliance, and it's kind of layered through that. So it's easy to understand and it fits well with a lot of organizations. All right, I don't think anyone's gonna answer any questions, so I'll just go to the next one. Cool. All right, event-driven architecture. All right, so this is kind of a distributed architecture pattern. There's two main ways of thinking about it, mediator and broker. So event-driven architecture, I think, has gotten a lot of good attention recently. I say recently, but probably over the past 7 or 8 years, a lot more people have been talking about events and event-driven architecture and having event stores and that whole like CQRS into event store like pattern is super interesting. It does create kind of a distributed nature to how we're breaking up the software. It's adaptable. These two particular patterns, mediator and broker. It's mediator, I'll say, / orchestration, because really the mediator is there to kind of actually call out, and we'll look at the particular patterns. And the broker is more of a choreography style of interactions for the events. So if we're taking a look at, no, it's okay. So if we're looking at mediator versus the broker, this is kind of what it looks like. An event happens in the system. There is some sort of, in the mediator orchestrator pattern, the event goes into some sort of queue, and then we have this event mediator. So you think about a piece of software that is listening for an event, and an event occurs, and you're like, okay, first I'm going to call my event processor 1, and then we're going to go to event processor 2, and when I get a response back from that, I'm going to 3 and 4. There is an order to it, and that order is being managed by that mediator. So there's kind of, this diagram shows, event channels. Those event channels could be other queues, or they could be direct connections to services or small applications that are running. Everything will continue to blur as we go through this architectural discussion, because if you look at this, you're like, oh, well, that kind of looks like how microservices would be put together. And that could be the case, but if we're thinking of this as a single application, they just may be processes, right? And we may have processes, and processes are listening to some sort of queue, or maybe they're not listening to queue at all. Maybe we're doing HTTP. But the core concept here is that there is, for the mediator, there is something in the middle that is talking to other processes and doing it in a specific order. Now, on the broker or the choreography style, what's happening is an event occurs, and anyone can respond to it, right? I mean, if you think about like a RabbitMQ or a different queuing technology, an event comes in and you're subscribed to that event channel, maybe Kafka or something, right? You're listening to it, and you don't know exactly who's going to respond to it, but the responsibility is on the event processor to pick it up. So there's less control, and sometimes you can get into these weird situations where you really, really, really would like to know what order things are happening in, and this choreography can be very complicated to try to get that ordering to occur. And so you may end up with something crazy like, okay, well, an event occurs to maybe place a bid on some auction site, right? And you want, well, let me use a different example. You place an order at Amazon, right? And the credit card transaction has to occur. We have to check our inventory and get a particular distribution center online to kind of pick the order. We got to figure out where we're shipping it to. We have to update our inventory. We have to notify the user that their purchase was successful. And so those all kind of happen in a distributed fashion, and we're not exactly sure on the particular ordering of them. But if we want to have the credit card transaction occur before we pick it and ship it, which might be a good idea, then a way to do that that's kind of kludgy in this broker or choreography pattern would be to have like a purchased event, and that purchased event then fires off an event that's like, pick and ship events. So you can end up with a lot of different events that are kind of coming off of each individual event processor queuing up a new event that's expecting in a different event processor. And that can be not the greatest because you have a ton of different events, and you're kind of using the events to try to do orchestration. So if you kind of see some of that feedback, maybe you should be looking at orchestration over that. Cool. So kind of pros and cons of the event-driven architecture here. So be able to respond quickly to changing stuff, right? Being agile, because each one of the event processors is kind of performing a particular piece of business logic. Making a change is easy because they're isolated, right? Their own little process, their own little program that are running along. Ease of deployment, because there's decoupling. We're using that either messaging infrastructure as a way to kind of decouple our processes. We can deploy individual units without impacting others. So again, the easiest example to kind of think of is a queuing technology, and you have a bunch of different event processors. You want to make a change to one of the event processors. It doesn't necessitate that you change the queuing, and it doesn't necessitate that you change any of the other event processors. Testable, like I was talking about before in the choreography kind of design pattern there, that it can be really hard to test because it is an asynchronous system. It's a little bit easier to test in that mediator kind of orchestration workflow, because you're blasting out messages, and the human mind kind of expects things to execute in a particular order. And when we enter into this multi-threaded asynchronous world, that is not how that works, right? So it can be very difficult and complicated to test. There are some things that we kind of do to try to keep track of how messages are flowing through the system, and there's a lot of interesting tooling out there now as we have more of an asynchronous world with distributed computing. The basic stuff, right, is creating a correlation ID that gets passed along with every one of your events. That kind of gives you some way to trace through where all of your event processors are dealing with a message. So again, that Amazon order comes in, and it's going to create a bunch of different events for a bunch of different event processors that need to happen. We're going to put an ID on that first event, and that event, as it explodes out into different events, we're going to pass that ID around. And what ends up happening is after everything is over, then you can go through the logs and kind of figure out how it processed through your kind of asynchronous environment. So it can be very difficult to test, which is why testability is kind of difficult. While you do have that isolation, it's the collaboration between the processes that make it difficult to test. Performance, I don't know if anybody's ever used a queue as a way to expand out your performance, but there's some scalability there because we can have queues that are giving us round robin processors. So we have 5 processors listening to one particular channel. Then they can round robin style that, so distribute the computing, makes the performance better. Scalable, naturally scalable through these independent decoupled pieces. Again, we can add more there. So ease of development, this can be kind of hard for people as kind of correlated to the testability, right? It's hard for people to see how things are flowing through. And so that makes it difficult for them to develop because you don't want the situation where in order to make a change to one event processor, you need to understand how all the rest of the event processors are working. And that may be kind of a smell and a piece of feedback you want to take into your architecture. Cool. Microkernel architecture. So this is also called kind of the plug-in architecture. I think almost everyone in this room has used this architecture, whether you've known it or not. If anybody's used Chrome before, those are plugins. If anybody has used like a VS Code or a code editor before, that's a plugin architecture. Right, you add features. You create extensibility through adding these features. There is some isolation there. The core system is really what is the kind of the complicated part and the complexity of this particular architectural pattern. So there's two main pieces of it, as we kind of showed in the previous slide. There's the core and the plugins. So while we all have used this architecture in our daily lives with browsers and code editors, I would bet that not a lot of you have come across this in kind of the custom business application world. And the main reason behind that is it is very hard to create a core, right? If you think about a web browser, the main function of the web browser is to serve up web pages, right? All the other extensions that we add in, whether we're want to get access to the JavaScript editor, or we want to put in shortcuts for specific keys, or we want to do something cool, those are all in extension to that core concept of serving up web pages. Same thing with a text editor, right? If you think about, I think one of the reasons why VS Code or some of those other lighter weight text editors have been so popular is that you don't get the bloat of a giant IDE. You can put on the things that you want. You can add things to that system, but the core is to edit text, right? It's much, much harder, I think, if you try to have that concept implemented in a business context. I think businesses kind of view their core operations as constantly changing. But this architecture pattern is interesting from the perspective of, how do you add new features to it, and having a core that has an idea of like a plug-in registry, and that's built into the core, right? That we're adding new functionality in. So the core is, what does your business do, plus a registry kind of function that then will load up whatever plugins are available to them. So this is kind of similar to, at least conceptually, the idea of like feature flagging, right? And maybe a way to do feature flagging or to do features would be to do this style of, I have a registry and a core, and here's how I add a feature to my system, and maybe that feature is not necessary for all my clients, but kind of depending on what they have opted into, they get that functionality. So as far as kind of like pros and cons of this pattern here, right? It is agile, right? It is quick to change as long as we're not changing the core. We have to be very, very protective of what is going on in the core because it has a large impact on the system, right? If we have a good solid core, then we can make changes and add plugins as we need them. Ease of deployment, as long as we're adding plugins, right? We have a plugin registry. We just kind of dump the plugins in and kind of away we go. Testable, as long as we're talking about testing individual plugins. Easy to go, right? We can mock out what the core is doing and how it's interacting. Has anybody ever written an extension for one of their IDEs or Chrome? There's a couple hands going up. Hopefully it's somewhat easy to kind of see what those API calls were coming from the core and kind of mock out what was going on and see the value of what you're doing. Performance, I wouldn't call this super performant, but just like VS Code, if you don't have to have all the functionality you don't want, you can kind of get your perfect balance of all the features that you need, which can give you some performance. I think if in more of the monolithic world where you're installing a giant IDE, I think we've all experienced how slow that can be. Scalable, the core is small and is usually deployed as one particular unit, so it's hard to scale. We usually think about these things as end user applications. I have not had a ton of experience creating products, but I think this fits, this architecture pattern fits in much more with product offerings that are kind of given out to clients. So it's not particularly scalable. That core and understanding the core and being able to make good decisions about the core makes it not particularly easy to do development. I think if anyone's had the experience of a business feature that comes in, you're like, no, that doesn't fit in this piece of software, and usually the business will come back and be like, well, we need to have it fit, and let's go. You have to be very disciplined about keeping the core separate from the other plugins that are happening. All right, so this is usually the one that everyone's excited to talk about. So just take a break. Microservices. Has anyone heard of microservices before? Okay, I'll take that as a yes. Cool. All right, so microservices is an interesting architectural pattern because it very much is mixed in with a bunch of other concepts. It kind of grew out of the necessity of organizations to manage the complexity of much, much larger applications that need to be scalable and need to be deployable. Usually the first question is, what the heck is a microservice? How do you define it? Why is it different than service-oriented architecture? Why is it different than anything else I've ever done before? And that's the fun part, right? So kind of the unconsensus consensus is an independently deployable piece of code that is the right size as far as complexity, not too big, not too small, just right, like Goldilocks. And that's pretty much it. It's independently deployable, and it's not too big, and it's not too small. So kind of the goal here, right, is to separate out your logic into services where service owns that logic and, in an ideal world, owns the data. It is an evolution, again, of kind of those different patterns. And the idea is we kind of follow that single responsibility idea from software development and solid and at a much lower level and kind of bring it up into the architectural space of each service component or each microservice should have a single responsibility. This is often how we see microservices these days. We have some sort of client that is making a request to some sort of API. In kind of the more modern patterns, we're seeing this API being an API gateway. And some of our cloud providers, Azure or AWS, they have these as offerings. That API gateway is there to do some interesting stuff beyond just kind of route to the individual microservices. But in this particular pattern, right, we have the external talking to some sort of API. That API is then often orchestrating which microservices it needs to talk to. It talks to those microservices, gets a response back, and sends it back to the client. We're looking for, again, those fine-grained single responsibility services. This particular one is looking at it as each microservice is REST-based. So each microservice then is its own little API. Cool. So we can also do this same style in kind of a thick application, something that's installed on a particular machine. In this case, right, we are pushing some of that logic to the client to have them talk to the individual service components that they want to use. They are, again, following kind of the same patterns and kind of using REST. And then this last one is really about, this is kind of the merging of the API gateway with the reality that we may not always want to use REST to do this. So this is where we start to merge in the idea of the event-based with kind of microservices architecture. So we can do interesting things like like distributed transactions. We can do just general channel and event-based architecture in the microservices space. The difference between this microservice architecture and the event-based one is just kind of the scale at which we're talking about. And the event-based one, it could be like one program with a bunch of different like little processes, maybe little threads hanging off it. This is a bunch of processes that are now communicating with each other. They can communicate API, they can communicate in files, they can communicate by passing messages through databases, although I would not recommend that. They can also use queuing technologies to kind of do that communication between each one of the microservices. Okay, so there's two things that are not obvious and I think are very important when dealing with microservices. I think the first, which we kind of talked about briefly before, was the granularity of the microservice. If it's too large or too coarse, it's like having mini large monoliths, and you're not getting the advantages of continuous deployment of these independently deployable services. There's not loose coupling. It's hard to scale. It's hard to test. If it's too fine or too small, right, then it just leads into kind of a bunch of processes. So there's an interesting saying out there which people should take into account is the real value of microservices is taking a simple business problem and turning it into a distributed computing problem. So we think of these very much, these microservices like, oh, it's awesome. It's only going to do this one thing, but it needs to talk to another thing, right? It's going to have to talk to another microservice. If you can get away with a simple problem that is like 4 microservices and they don't have to talk to each other, awesome. But in the reality, the world is complex, the microservices are complex, and you are going to have to interact between them, and you're going to have to deal with stuff like distributed transactions. How do you deal with a distributed transaction? How do you make sure that if service A does something and then service B does something and service C fails, that you undo what happened in B and C? Let's take the Amazon order. If we create an order for Amazon and we charge the credit card, and then it goes out to inventory and it says, oops, I don't have that in inventory, we need to be able to credit them back the money that they had, right? Because it's now kind of a distributed architecture that's asynchronous, now you have to do stuff like compensating transactions, and you have to do stuff like sagas and orchestration and choreography around these larger transactions. So it becomes very, very complicated. So between the complexity of understanding the distributed computing impact of the microservices and getting them the right size, and creating the just right size of the microservice is, so the way I found this to be successful is twofold. One is to kind of take some of those domain-driven design concepts around a bounded context, and that is very much an exploration of kind of how we communicate and how we form ideas. And I know that's a very highfalutin way of saying it, but the idea of a bounded context is about how words are defined in our business and how we talk about those concepts as developers, and when those definitions of those words begin to change. And when those definitions of words begin to change, then we know that we're close to a boundary. So when we're looking at this single responsibility idea that we're encapsulating inside this microservice, we should be looking at, what does it mean to have, let's say for an example, an account. The idea of an account can mean a lot of different things in one organization. An account could be your identity access and management account, or if you're dealing with something financial, it could be a financial account, right? Those two words have distinct meanings in different areas, and that's an example of where they should be separated into their own microservices. That's a pretty easy example. If you think about it, you don't want your identity access and management to be encapsulated in one microservice that's dealing with the idea of how much financials you have in an account, right? Those two concepts are separate, same word, that's the general idea. First, we use this idea of bounded context, and second, we incorporate the ideas of DevOps, which is feedback. So if you deploy these microservices, You should try to get them out as quickly as possible and kind of get some feedback on how chatty are they. If there are two microservices that are constantly talking to each other, should that be one microservice? It's a good question. If there are no communications coming out of a microservice, okay, maybe it's too big. Is everything going to one data store? That can be a problem as well. So kind of the pros and cons here of the microservices. So Agile, yes, this kind of fits in with the whole concept of it being kind of DevOpsy and Agile. Single responsibility related to each one of the microservices. Make a change to that single responsibility, deploy it, cool, Agile. Ease of deployment, again, that's kind of built into the definition. This is what we're striving for. We want these microservices to be isolated from the other microservices so that they're testable, so that they're easy to deploy, so they kind of fit that mantra of single responsibility. Here's the one that people most don't realize is the performance impact of it. And this is a piece of feedback for how your microservices are working. There is, I think, the perspective out in the development world that microservices are the way to go every single time. I would not recommend you necessarily doing that. I think you need to take your problem space and figure out if this architecture is going to fit with what you need. But every time you're making a call to another microservice, you are taking what used to be an in-process communication, if you were in a monolith, and making it into a network call. So there is latency involved in that. If you have 100 microservices that you are talking to, you are adding 100 network latencies to a single call. This fits into the granularity piece as well, right? What are the performance requirements of your system that you need to take into account? Maybe you need to smush together some of this data, some of the microservices responsibilities, and maybe you need to smush together data. Maybe you need to do these other pieces, but just in general, taking a problem and making it into a distributed computing problem and introducing network latency can have a serious impact on your performance. Super scalable. You can have a bunch of these microservices all kind of functioning as, dealing with that one single responsibility, and then put some kind of load balancing where we can do stuff like event processing, with the idea of putting a queue and having multiple kind of processors kind of deal with that message or that event and do the logic that is necessary. Ease of development, because we're keeping those boundaries pretty tight and understanding smaller scope. There's some anecdotal measurements around microservice. Think of that as what you can redevelop in like a month, right? Something you can redevelop in a month. So the scope is smaller, and so it's kind of easier to understand what is its responsibility and what is what needs to change in order to make the new kind of functionality work. All right, so the last one, space-based architecture. My guess is that most people have never heard of this. This is very, we're going to go through the individual components of this. This is an architecture that is designed very much for scalability as the problem. It makes decisions that you will see in other architectures, and it tries to solve some of the problems that we see with microservices and how you would go about tackling them, which is why I think it's a particularly interesting microservice pattern. You would only, I guess you would, unless you have a lot of money, you would mainly be doing this in the cloud. All right, this can be very complex and expensive. All right, so here's kind of the pieces of it. There's this idea of a virtualized kind of middleware and then individual processing units. So each one of the processing units could be an identical copy of what is going on for your application. So if you have a website that is going to have like a trillion users that are going to come in all at once, then you would have copies of that website as individual processing units. The kind of middle layer here, or the virtualized middleware, has particular responsibilities, but kind of request comes into the virtualized middleware and then gets routed to the appropriate processing unit. The processing unit responds to it, makes any sort of modifications to the data store, and then responds back to the original call. So a lot of the stuff that you're seeing here at the bottom, you'll see kind of these processing units. I don't know if okay, yeah. These processing units are kind of talking to each other. It's kind of out-of-band synchronization of the data that's kind of working. So this is definitely like an eventual consistency style model where we are pushing everything closer together. This reminds me a lot of I don't know if anybody's done computer architecture, but you think about your processors. We have processors, and then we have L1 and L2 cache. That's about getting information closer to the processor. And then beyond that, we have memory, and beyond that, we have disk storage. Right? This is very much about how do we get information closer to the processing units, so we don't have to incur latency for talking to that. So this is kind of a zoomed in processing unit. So the application logic is going to be in different small modules, different pieces of code. We are talking to an in-memory database, and I forgot to mention something, but the term space-based architecture comes from the idea of tuple space, and tuple space is the idea of tuples that are stored locally, which is an ID and a value. And so this main architectural component is having a tuple store that is close to, so you're not having to go out and get information, to the processing units. There is an optional like asynchronous persistent store. So these are ephemeral. So if you want to save that data off and make sure that it's not destroyed when this processing unit goes down, then kind of an asynchronous pattern that is recording what's happening in in-memory database. And then there's a separate process that is doing data replication. So if you think about an event that's coming in, something has occurred, there's a request, it's going to hit the processing unit, it's going to go through the modules. The modules are only going to be talking to this in-memory data, and they're going to respond back. And out of band, there's going to be like the impact or change to our data is going to be, let's say, persisted to something long-term, but it's not part of that initial transaction. And then, oh, by the way, I'm going to let my other processing units know that there's been a change, and then they need to react to that change. So here's what the middleware kind of looks like. The messaging grid, it's in charge of managing those input requests and figuring out which processing unit to use. So if you have a bunch of different processing units, what you're going to want is each one of those processing units to say, hey, I'm busy or I'm not busy. And the messaging grid, its responsibility is to figure out which one to use that's not busy now. And so here's the work. Go do that work. The data grid is managing that replication that's happening behind the scenes. What happens if there's a failure between that? Do I need to roll things back? What are my responsibilities there? That's what the data grid does. This processing grid is conceptually is doing that distributed transaction work. The piece of software that's managing if one of the processing units fails. This is where, again, things start to blur. Is if you think about these individual processing units as microservices, like this would be the layer that would be kind of managing all the microservices. So that could be something like an API gateway that's doing some of that work. And I'm going to talk about some other ways that we kind of solve these problems in the real world. And then the last piece of this is kind of the deployment manager. When are processing units failing, and when are they coming up, and when do they need to start, and what are their response times, and all that kind of good stuff. So conceptually, these are all kind of the responsibilities of that virtualized middleware. So in like actual implementation, this is very reminiscent of container orchestration, right? Our Kubernetes that's out there, our OpenShift. These are the type of responsibilities that a Kubernetes is trying to take on. So like a deployment manager, Kubernetes, you're saying, what number of these services do I want up and running, and what happens if one of them fails, right? The processing grid stuff is probably a layer down as far as being able to orchestrate, distributed transactions. Managing data replication is the idea of like data pumps. Messaging grid and how you're routing stuff. Kubernetes can take care of stuff like that as well. So these are good concepts to understand, but understand as we get into larger scales and we talk about containerization and container orchestration, the goal of a lot of these frameworks like Kubernetes is to take away those responsibilities from you or to create an easy abstraction for you to understand. But you should understand under the hood what it is that they're trying to do. All right, so agility, right? The processing units can be brought up and down pretty quickly. You can make a change to them. You're deploying just one thing. So as each one individual processing units are separate, the testability gets kind of a thumbs down because this is a scalable architecture. So if your goal is to see how scalable it is, it can be very expensive and difficult to see what is the final load that you can put on the system. It is built for performance. It is built for scale. The ease of development, you have to take into consideration what are all of the implications of your changes to the software for its performance, for its data replication, for its how all the pieces kind of work together. So you have to keep a lot of concerns in your head, which makes it kind of difficult for developers to understand all of the trade-offs they need to make. So as just kind of a wrap up to this, as we went through and we talked about microservices, we talked about space-based, we talked about microkernels and plugins and event-driven and layered, they're all very much related. They're all very separate as far as what is their value statement, but when you're implementing an architecture that's going to solve your problems, my goal for this talk is for you to be able to speak about these or to understand that they exist, these different architectural patterns and kind of their pros and cons, so that when you get to a problem space, you can say, oh, well, I really want to do microservices because those are super cool, and we should do it in containers because containers are awesome, and it makes it easier for me to develop, but now I'm going to have to deal with distributed transactions. Oh, that was kind of a little bit like event-based. Should I be using kind of orchestration, or should I be using choreography to do my distributed transactions? And, oh, this particular one needs to be really fast. Maybe I should put a key value store as a data store and then maybe use like data pumps. I'm going to pull some things in from space-based. I'm going to pull some things in from microservices. I'm going to pull things in from plugins and microkernel and event-driven and layered and kind of come up with the best solution. So that was the talk. It wasn't as interactive as usually this particular talk is. If anybody has any particular questions, feel free to come up and chat with me. I'll be around all day, or you can hit one of these social things. Okay, thanks everyone. I appreciate it.